Hey everybody, this is me making a quick, or hopefully quick, tour of the unit test for sequences and series. Try to go fast and we'll see if we can get her all done in like 10 or 12 minutes. All right, here we go. Okay, well, thanks to Bob Ogden, I got a Wacom tablet and I have the ability to pause. So what I did with this was I thought of it as this expansion. And then if that's what f of x is, then to integrate, I integrated each term. So I went from 3 over 2x squared to then I took that 3 and I put it back up in the exponent. I just went term by term and integrated. And then remember, we're just evaluating this definite integral from 0 to 1. So in place of every x, I put a 1. And then when I put a 0 in, that'll just become 0. So it is not easy to see right off the bat, but it boils down to a simple geometric series with a lead term of 1 and a magic multiplier of 1/2. So that turns out to be 2. It should be 2. Let's hope so. Okay, that last one was an example of one that was pretty tough. This one is very straightforward. It's just 1 over n raised to the 1/4 power. 1/4 is nowhere near being greater than 1. That is definitely divergent. Divergent. Next one. What are all the p-values such that this is convergent? Okay, so that's an alternating series. So we need p-values that are going to be such that this diminishes to 0. And since it's alternating, it will converge if the individual terms go to 0. So looking at this denominator, I just want to make sure that it is not less than 0, or if it's equal to 0, if that exponent is equal to 0, just be a number, and that wouldn't converge. So I need p to be slightly bigger than 1. So that would be this one right here. If it's equal to 1, we're in trouble because that's n to the 0. Okay, now here we've clearly got a ratio test. So I'm going to pause and just write it out and you can take a look. Okay, so I've written this out now and you can see that we've got one more 9 down here than there is up here because there's n plus 1 of them down there. So I've got just the 9 left here. And I've got 2n plus 2 plus 1. That's 2n plus 3. And here I've got 2n plus 1. So I'm going to have 2 more 3's, or that's in multiplying. So I'm going to have 9 right there. I'll have 3 squared right there. And then these guys will go to 1. And that means that 3 squared over 9 goes to 1. So this equals 1. So that my limit right there is going to equal 1 if I've done that correctly. And that is not conclusive. We just don't know what's happening. So we're going to say that in the ratio test, we need it to be less than 1. Equal to 1 is inconclusive. All right. So using the alternate series error test, what's the least number of terms necessary to approximate this series within? All right, so I'm going to write this out again. Okay, so this is similar to one we did in class. We've got a square root in the bottom, and we want to look at the next term after the last term for that error. So we do that last term, k plus 1 in the square root equals to our bounds for our error. Just remember that you're really looking at being more accurate than this. I think that you can get away with not even really thinking about the greater than less than. Just think of it as k plus 1 equals 1,000. When you solve that for a million, take away 1, that's the k step that will get us there. So it's 999,999. Hopefully that is correct. Okay. Then this is our Lagrange error. That is not going to be on the quiz. But while we're on this, I'll show you kind of the quick and the efficient way of making an educated guess, and then we can go into it in detail a little bit later. Okay, this is that Maclaurin and Taylor polynomial error, the Lagrange error. And the formula is a little bit funky. It's got 3 parts to it. It's got this numerator part, which is the maximum of the n plus 1th derivative. So whatever your function is you're approximating, in this case it's an ln function, and they've given us the little formula here for the derivative. The nth derivative is this formula here. And you can expand it out and do it on your own. But there's the formula that's telling us about the nth derivative. And this is the maximum value that can be found in the interval from where you're centered 1 to 1.4. So in there, this maximum value is going to happen in a fairly narrow range, but since we've got our x value in the denominator, it's going to be the largest one. That's the smallest value. So I'm going with 1 on that. And then it just kind of drops out. And if that drops out and you put this nth derivative right here, you've got this formula with n minus 1 factorial over then the formula for the error has got an n plus 1. That's like the next term, like alternating series. We're talking about the next term in a Maclaurin series. You've got the n factorials down below, so the next one is n plus 1 factorial. And then this is all about that centering, which we, again, looks familiar from the Maclaurin and the Taylor polynomials, but it's not to the n, it's to the n plus 1. And I just subtract that value, that x minus, in this case, 1.4. So that's where 1 minus 1.4 comes up with 0.4 right here. And I'm going to go to a different color. And so when I go to the third, when n equals 3, now here's 3, and then 3 plus 1 is 4, and I'm multiplying these because why? Because this n minus 1 in the numerator, if you think about it, if it's factorial, n minus 1 factorial is going to cancel with all of the things after n plus 1 times n, then times n minus 1, and so on, because that's going to cancel right here with this and leave just the n plus 1 times the n. There's the n plus 1, and there's the n. And now it's just kind of like guess and check. I can just try these different values. And in looking at this, I think that I can get it after the fourth one. So I'm going to go with this. If I'm wrong, we'll just quickly look at the answer and we'll see where my mistake is. So we're just going to quickly get help and then see what I did wrong. That is, I'm just going to leave this here. You can take a screenshot. Okay, so it wasn't 4, it was 5. All right, well, there we go. I needed to go one more step. All right. Find the third degree Taylor polynomial centered at x equals 1. Okay? So, okay, it took a moment here to write out the function and then its first few derivatives, first 3 derivatives, because it's a third degree there. And so if it's x to the minus 2, then it becomes minus 2x to the minus 3, and then minus 3 times the minus 2 gives you positive 6x to the minus 4, and so on. As you look at this, then it looks like when we've got our everything's, the 0th power, we're going to get 1, but then we are going to get a minus 2. Here we have 2 candidates for minus 2. Then which one of these is correct? Well, if it's centered at 1, it's x minus 1. So this looks like this is our best candidate. It's alternating. It's doing everything we expect. All right, moving along. Find a power series. Okay, so this one is also worth writing up a little bit. Okay, so I just wrote out the basics of a geometric series, that it's that magic formula of the first term all over 1 minus r. That will be what's equivalent to this expansion of that first term, and then each time added on with an additional multiplication by the common ratio, the magic multiplier r. So if you follow this pattern then and you plug in the 4 for a naught and you plug in minus 5x cubed, because we need to be able to subtract a minus 5x cubed, then I think you'll see that it's going to be this one here. We've got 4 and then negative 5 times 4 with x to the third matches. And then when you square that, you're going to get positive 25x to the 6 times 4. So I'm going with that one. Okay, next one. The nth partial sum. What is the total? That's going to just let n go to infinity. Clearly, the n's in the numerator are winning. This guy diverges a few seconds. Okay, I hope they are all that short. find, or here is the Maclaurin series, find f of the ln of 7. Okay, oh, and looking at this, this is actually 1/2 of x to the n over n factorial. That is the Maclaurin expansion of e to the x. So this is actually just e to the x over 2. Does that make sense? If you look at that, you should really memorize the 3 most common Maclaurin expansions. That's e to the x, sine of x, and cosine of x. Okay, and this is just all of this. It's x to the n over n factorial without the 2. And so with the 2 there, it's 1/2 of that. All right, so then what is e to the ln of 7? Well, that's 7, and half of 7 is 3.5. What conclusion can be reached by using the nth term test? If we take this out to infinity, it's 1 over n. It's essentially 1 over n. And that does go to 0. So we can conclude that the series that the series behaves like 1 over n, which is unfortunately inconclusive in this case for the nth term test. What is the interval of convergence on this one? Okay, well, if we just do that ratio test, we can solve then for the interval of convergence. Okay, now I've had a moment to write this out very poorly, but using the ratio test and very carefully putting in n plus 1 and then doing some cancellation, you can see that I've got an n plus 1 over an n. As n goes to infinity, those just balance out. That plus 1 isn't going to amount to anything, so that just cancels. Negative 2 over negative 2, that's just going to cancel. But the x plus 6 plus 1, there's one more x plus 6, so that's why that's there. And then there's also one more negative 5 in the denominator, so that's why that's there. And then, of course, we're interested in knowing when is this less than or equal to 1 in its absolute value form. So when I split that into negative 1 and positive 1, and then multiply by a negative 5, the negative 1 becomes a positive 5, and then the positive 1 becomes a negative 5, but that's x plus 6, so then I subtract 6 from both sides. So then I get this, negative 1 less than or equal to x less than or equal to negative 11. So if I sort of switch that around, you can see that's my bounds here. So I know it's going to be something like this, but then I want to check the endpoints. So if I plug in negative 11 up here, you can see that becomes negative 5. Well, negative 5 to the n over negative 5 to the n, perfectly balanced, cancels out, and I get negative 2 over n. Well, that's a harmonic series, and that's not going to work. So we do not want that to be equal to negative 11. If I plug in negative 1, however, now I've got a positive 5 and a negative 5, and that's a difference of a negative sign. So it's like an alternating harmonic series, which does converge. Alternating harmonic series do converge. So I want it to be equal to negative 1, but not equal to negative 11. So this should be good. Yay. When applying the integral test, we get a limit that determines whether the series diverges. What is that limit? Okay. Okay, so again, I've written out the basic concept here that we're integrating an exponential with a base that's not e. So it helps to sort of think about what would you do if you're integrating e to the negative x? Well, that's just going to be negative e to the negative x. It's a lot like if you're taking the derivative. You just have to think about the chain rule. And with e to the x, it's a chain rule going forward or in reverse. When it's not base e, remember there's this adjustment factor. And so if we're taking the derivative of a to the x, you get a to the x times the ln of a, whatever that base is. When you're doing the reverse of that, you've got to put that in the denominator, because when you do it over here, when you take the derivative, you need that to cancel out. And in this case, you need to cancel out also a minus sign. If there's a minus sign, then we'll have a minus sign here. So this is the integral then of 5 to the minus x. It's that minus 1, ln of 5 to the minus x. When you plug in b first, you've got a negative term, and then you plug in 1, and you're subtracting then a negative term. So you can just reverse the order and reverse the sign, and I think it looks like A. So let's keep our fingers crossed. Yay. Few left to do. Here we go. Which sequence converge to a limit as n goes to infinity? All right, so this is a battle of numerator and denominator. If I make this be 5 squared to the nth power and 4 to the third to the nth power, that's 25 over 64, which is less than 1 to the nth power, so that is going to converge. Here, if I do the same type of reasoning, 2 squared is 4 raised to the nth power. Think about your rules about exponents. And 4 over 3 is bigger than 1, so that's going to diverge. And n factorial is definitely going to converge. So which sequences converge? Those two do. Okay, now we've got a comparison. All right, if we're looking at this, you could ignore the outer bits and key in on the degree, and that's n squared over n to the third. There's a difference of only 1, so we want to compare it to the harmonic right there. And we know that the harmonic diverges, okay? So if this is less than a divergent one, that doesn't help us an awful lot. We need something to be more than one that diverges, so this test is inconclusive, okay? Think about that. Next is a power series, okay? Use this fact to find the power series here. Okay, what's going on? Let's talk about this. Okay, well, actually, I don't think that you need to write out a lot, because what's really going on here is we've got a 1 over 1 plus x. So that's the same as 1 plus x to the minus 1. And a lot of times when you ask a question like this, it's really all about, are you understanding that you can integrate and you can take the derivative of each term of an expansion to get the integral or the derivative of the thing that's giving you that expansion. So if you look at this and if you rewrite it like this, well, if I take the derivative of this, remember we just used the chain rule, I bring that out front and then I kick it down a notch, I multiply by the derivative of the inside, which is just 1. So I will get this, except that it's missing that minus sign. So in a sense, I can just take the derivative of each of these terms and then change the sign, and I'll have this positive 1 power series. So if I take the derivative of that, I get 0. If I take the derivative of that, I get a negative 1. If I take the derivative of this, I get a positive 2x. The next term will be x to the third that's negative, and so I would get then for my next term, I'd get a minus 3x squared. But remember, we're reversing the sign on this. So I'm going to look down here and see which one of these is reversed all the signs, and that looks like it's D. All right? So that is good. And I'm looking at the time, and I've gone over 15 minutes, so I'm afraid I can't post this on YouTube if I go too long. So I'm going to stop this and then upload it. I hope that will get you close to the end, folks.